Okay, test the leg, everybody. So, in today's video lesson, you're going to learn about particle nature of electromagnetic radiation. In fact, in the last two video lessons, you learned about the wave nature of electromagnetic radiation. And now, as far as the particle nature of electromagnetic radiation is concerned, now you will see that the scientist by the name Max Planck, way back in 1900, in fact, played a very important role. So it was Max Planck who gave a very concrete explanation regarding the particle nature of black body radiation and photoelectric effect, because the electromagnetic wave theory could not explain these, that is black body radiation and photoelectric effect. That is the experimental results that were obtained from these experiments, right? Black body radiation and photoelectric effect. Now, the thing is that whenever objects are heated, they emit radiations over a wide range of wavelengths or frequencies. This is what is observed. And now you can see that when an iron rod is heated in a furnace, what happens is the iron rod initially becomes dull red in color, and then as it is heated further, it becomes more and more red with further increase in the temperature. And when it is still heated further, it becomes yellowish in color. It becomes, then after that it becomes more whitish in color, and still, with further increase in temperature, as you go on heating it, it finally becomes blue in color. So all this is because of the fact that this iron rod, when it is heated, from a lower temperature to a higher temperature, it actually gives out radiations or having different wavelengths. And as a result, you see that the colors that we see of the radiations emitted, they keep changing. This is what is seen. And now, it's important to know that the frequency, or as far as the frequencies are concerned, you will see that the frequencies of the radiations emitted, they actually, go from lower frequencies. That is, the frequencies of the radiations, they go from a lower frequency to a higher frequency. And the lower frequencies are seen in the case of the red color, right? Red color component of your visible light. And then the higher frequencies are seen in the case of your blue color component of your visible light. So these are the things that are actually observed. Now, the important thing here is with regard to what is known as black body radiation. Now, as far as black body radiation is concerned, you should first of all know what is meant by black body. So, an ideal body which can emit or absorb all frequencies of radiation is called a black body. And the radiation emitted by such a body is called black body radiation. So, It is actually an ideal body, a perfect body. So an ideal body which can emit or absorb all frequencies of radiation or all wavelengths of radiation is called a black body, and the radiation emitted by such a body is called black body radiation. Now, with regard to the black body radiation, as I explained just now, what is seen is at a given temperature, like you can think of the iron rod as it is heated, where the temperature is kept constant. And if you were to plot a graph of wavelengths or the radiation against the intensity, you will see that, say if this is taken as the wavelength, on the x-axis you have the wavelength, and then on the y-axis we're going to take the intensity. Okay, you have intensity here. Intensity of the radiation. Now let's take this like this. And then you're going to have the intensity of the radiations emitted. Now it is seen that at a given temperature, like you're going to keep the temperature constant, what you will see is with increase in the wavelength, as the wavelength increases, you will see an increase in the intensity, that is intensity. Increase in wavelength, that is increase in intensity. Increase in wavelength, that is increase in intensity. And finally, the intensity becomes maximum at a particular wavelength. This is called lambda max. Let's call this lambda max. Now this is happening at a given temperature. Let's call this temperature T1, right? So at a temperature T1, as the iron rod is heated, you're going to keep the temperature constant up to some time, and then once it is noted, you're going to see different colors of light, right? Now at a particular temperature, what happens is the temperature is kept constant. With increase in wavelength, you will see the intensity increasing first, then it reaches a maximum at a particular wavelength, we call this lambda max, and then with further increase in the wavelength, the intensity is seen to decrease, right? It decreases like this. Alright. This is what is observed. And now, if you increase the temperature further, say to T2, then what happens is again the same thing is seen happening. Like with increase in the wavelength, there's going to be increase in the intensity. There's going to be increase in the intensity. So as the wavelength increases, intensity is also increasing, and then you reach a maximum intensity here, and you have your lambda max. This is the maximum intensity that you get at this wavelength called lambda max. So this is the peak intensity. So here this is happening when the temperature is T2. Here the temperature is greater than T1. Here T2 is greater than T1. And then again the same thing is observed. When you increase the temperature further and then keep it constant, then at another given temperature, let's call this T3, intensity is going to become maximum. Sorry, this is T3, and then here you call this lambda max. That's it. So now what is seen here is this is something strange actually. You can explain it as this way: with at a given temperature, with increase in the wavelength, the intensity increases. Then the intensity reaches a maximum at a particular wavelength, and then with further increase in the wavelength, the intensity decreases. Or else you can take it this way: with decrease in the wavelength, with decrease in the wavelength, wavelength is here, with decrease in the wavelength, intensity increases, and then after some time, the intensity reaches a maximum, and then with further decrease in the wavelength, intensity decreases. This is what it's saying. So this is something difficult to explain. Now, if you go according to theoretical calculations using this, energy, which you will see now, E is equal to h nu, the graph will not be like this. With decrease in the wavelength, you will see that intensity increases. That's fine, which means energy is also increasing, and with further decrease in the wavelength, actually frequency should increase, and then the graph will be going up something like this. So this is actually quite confusing. It's difficult to explain. So in order to make this thing clearer, to sort of get rid of this confusion or problem, Max Planck in 1900 he came up with this revolutionary theory called Planck's quantum theory of radiation. Now, as far as this black body radiation or photoelectric effect is concerned, these could not be sort of satisfactorily explained with the wave nature of electromagnetic radiation or electromagnetic wave theory, because in the electromagnetic wave theory, it is believed that energy is given out continuously. That is to say that when atoms or molecules, when they're heated, they sort of give out or they absorb energy in quantities which cannot be sort of measured as such. They can be any value, that is the radiant energy which is either absorbed or given out, maybe in any value from infinitely small to infinitely large as such. So here Max Planck, in his Planck's quantum theory of radiation, it is said that radiant energy is not given out continuously but discontinuously in discrete quantities. So this is what you're going to see now. So let's see, Planck's quantum theory of radiation. See, the electromagnetic wave theory believed in the continuous generation of radiant energy. So here it is said that as far as the electromagnetic wave theory is concerned, energy is generated. That is radiant energy. It is generated continuously. As I said just now. And it can be in any value from infinitely small to large. And now this theory, it could not explain the experimental results of black body radiation and photoelectric effect. But then Max Planck, he gave his revolutionary theory here, as I said just now, and according to his quantum theory of radiation, Max Planck's quantum theory of radiation, the main features are, the very first point here says, radiant energy is not emitted continuously, but discontinuously in the form of small packets of energy called quanta. That is the plural form of quantum. And then each such quantum is associated with a definite amount of energy. So he said there is a definite amount of energy which is associated with each quantum. Now, in case of light, each quantum of energy is often called photon. That's it. Now here, it's because this plot or graph that you see here, it created a lot of confusion regarding the maximum intensity here. With increase in the wavelength, you see the intensity increasing. And then again, with further increase in the wavelength, you see intensity decreasing, or if you take it the reverse way. So this was explained by Max Planck, based on these points, I should say. And here, one interesting thing you will see is that the frequency distribution of the radiation emitted from a black body actually depends only on the temperature. It depends only on the temperature. That's something interesting. And now the next point here is the amount of energy associated with a quantum of radiation is proportional to the frequency of the radiation or light. So here energy is getting quantified. Like you will see that the energy E that is associated with a quantum of radiation is said to be proportional to the frequency of the radiation or light. So E is proportional to nu, and when you remove the proportionality sign here, it becomes E is equal to h nu, small letter h here, where h is 6.626 into 10 raised to the power negative 34 joule second, and h here is the Planck's constant, and nu is the frequency of the radiation or light. And then this E is equal to h into c by lambda, because you have learned about the relation here between the speed of light and wavelength and frequency. You know that nu into lambda is c. So here when you replace nu here by c by lambda, you get E is equal to h into c by lambda, where now c is equal to 3.0 into 10 raised to the power 8 meters per second is the speed of light. And then the third important point with regard to Planck's quantum theory of radiation is the total amount of energy absorbed or emitted by a body will be some whole number multiple of quantum. So it will always be a whole number multiple of quantum. Quantum is nothing but the smallest amount of energy that is either absorbed or emitted in the form of electromagnetic radiation. So the total amount of energy either absorbed or emitted by a body will be, always some whole number multiple of quantum. So it's represented as the total energy absorbed or emitted is equal to n times h nu, where n is 1, 2, 3, and so on. Now the concept of energy packets of light, it supports the corpuscular theory of light. So earlier, it was believed that light was made up of particles. So based on that, there is this corpuscular theory. So the concept of energy packets of light supports the corpuscular character of light. It also explains the distribution of intensity of radiation from a black body as a function of frequency at different temperatures. So, to make things clear, Max Planck, he said that the intensity of radiation from a body, that is from a black body or any body for that matter, that is a function of frequency at different temperatures. So the intensity here, you see intensity increasing with increase in the temperature. So like here at this temperature T1, now here temperature T1 is actually lesser than T1 is less than T2. T2 is less than T3, which means T3 is the greatest temperature. Here T3 is greater than T2, T2 is greater than T1. So at different temperatures you will see the intensity to be different. So here it says that one minute please. Yeah. So the distribution of intensity of radiation from a black body is a function of frequency of the radiation at different temperatures. So the intensity is going to be different at different temperatures. So the intensity is a function of frequency of the radiation emitted from a black body or a body at different temperatures. So these are the important points that you are supposed to understand with regard to the main features of Planck's quantum theory of radiation. And now the next thing that I'd like to explain is about photoelectric effect. Now, as far as photoelectric effect is concerned, it is seen that certain metals, when exposed to light, they emit or eject or they give out electrons. So these metals like potassium, cesium, rubidium, etc. So when these are exposed to a beam of light, they sort of emit or eject electrons, that too instantaneously, that is suddenly. So this phenomenon of instant ejection of electrons from the surface of a metal, when a beam of light strikes it, is called photoelectric effect. So there is this experiment here, which was actually explained by Henrik Hertz. So here, as far as the photoelectric effect is concerned, you will see that there is this vacuum chamber like this. In the vacuum chamber, you have this metal kept here. This is the metal actually, and then it's connected to a battery here. You have your detector coming here. This is the detector, and then the detector is connected to an ammeter here. Then from the ammeter, it is connected to a battery here. You have the positive terminal of the battery, something like this. Now this is your battery, and then this is an ammeter here to see if there is any current flowing through the circuit or not. And this is the detector. Now, in fact, this is the positive terminal here. You have the negative terminal coming here. So now, when a beam of light strikes the metal surface here, okay, let's take it here. What happens is, soon after the beam of light strikes the metal surface here, electrons get ejected. So electrons are ejected, right? You have electrons getting ejected. So let's take this as the electron line. So this phenomenon here, in which you see instant ejection of electrons from the surface of a metal when a beam of light strikes it, is called photoelectric effect. Now, the results of this experiment were, see, the electrons are ejected from the metal surface as soon as the beam of light strikes the metal surface. So the thing here is that instant ejection of electrons takes place. That is, as soon as the beam of light strikes the metal surface, electrons are ejected from the metal surface. The second point to be understood here is the number of electrons ejected is said to be proportional to the intensity or the brightness of the light incident on the metal surface. So when you have a very sort of bright light incident on the metal surface, then there will be more number of electrons ejected from the metal surface. The third important point is, for each metal there is a characteristic minimum frequency denoted by nu naught. You can see there, this is nu naught, also known as threshold frequency. So for each metal there is a characteristic minimum frequency denoted by nu naught, also known as threshold frequency. So the minimum frequency which a beam of light or a photon of light should have in order to eject an electron from metal surface. It's called the threshold frequency. Now, if the frequency of the ray of light striking the metal surface happens to be less than the threshold frequency, then no photoelectric effect will be observed. So if I read it once again, for each metal there is a characteristic minimum frequency mu naught, also known as threshold frequency, below which photoelectric effect is not observed. This is what we are supposed to know. And then it says at a frequency nu, this is the frequency of the beam of light striking the metal surface. So at a frequency nu greater than mu naught, the ejected electrons come out with a certain amount of kinetic energy. So if the frequency of the ray of light striking the metal surface is greater than the threshold frequency or the minimum frequency, then the ejected electrons or these electrons will come out with a certain amount of kinetic energy. And then these electrons, they move towards the anode here, towards the detector. So if the frequency of the ray of light striking the metal surface, this is the ray of light here striking the metal surface, if its frequency is less than mu naught, that is the threshold frequency or the minimum frequency, then there will be no electrons ejected from the metal surface. Now if the frequency of the ray of light striking the metal surface here is greater than mu naught, then in fact photoelectric effect will be seen, or photoelectrons will be ejected from the metal surface, and these electrons here, they will move with this kinetic energy. And let's see the calculation part of it now. When it says a more intense beam of light, that is, if the light is of greater intensity, then it will consist of larger number of protons. So if you have a light of high intensity, it's going to have more number of protons, which in turn leads to greater number of electrons being ejected from the metal surface, as compared to that observed when a beam of light of weaker intensity is employed. So when you have a beam of light of greater intensity, it will have more number of protons. When you have more number of protons, then more number of electrons will be ejected from the metal surface, right? So if you have a beam of light of weaker intensity, then in fact there will be lesser number of photons, and less number of electrons will be ejected from the metal surface. And then it says, but the kinetic energy of ejected electrons does not change. The thing is that for a particular light, with increase in intensity, you will only see, an increase in the number of photons, which will result in more number of electrons being ejected. But the kinetic energy of these ejected electrons will be the same. So this is what is to be understood. Now, there is another explanation to this based on the energy of the beam of light striking the metal surface here, and then the amount of energy that is required to remove the electron from the metal surface. And here, this is according to Einstein. See, as I said just now, we talked about something called the minimum frequency or threshold frequency. Threshold frequency or minimum frequency, that is mu naught, and then frequency of the incident light. Frequency of the incident light, or the light incident metal surface, that is nu. And now, if nu naught is greater than nu, then no photoelectric effect. No photoelectric effect will be seen. There will be no photoelectric effect. Or this is same as saying, if the frequency of the radiation or light falling on the metal surface is less than the minimum frequency, no photoelectric effect. Now, if this frequency of light falling on the metal surface is greater than mu naught, then there will be photoelectric effect seen. Yes, photoelectric effect. What? Photoelectric effect will be seen. Okay, here you will not see photoelectric effect. Right? Okay, that's it. Now, as far as this experiment is concerned, it was Albert Einstein who gave a very sort of suitable explanation, that is satisfactory kind of explanation. He said, like, now you have seen from this Planck's quantum theory, saying that the energy that is associated with each quantum is given by E is equal to h nu, right? H nu. So now, see, when you have a light of frequency mu striking the metal surface, then the energy of that, light striking the metal surface is given by h nu. Now, from this energy h nu of, say, a photon of light striking the metal surface, what happens is, a part of this energy is used up for ejecting the electron from the metal surface, and that is denoted by h nu naught. H is the Planck's constant, nu naught is the threshold frequency, that is the minimum frequency, and then the remaining energy which is left over, it is given to the electron. It's given the electron as its kinetic energy. And now this is the explanation given by Albert Einstein. So this is the energy of a photon of light that is striking the metal surface. h nu naught, this is actually the binding energy. It's also called the binding energy. Or in other words, it's also called the work function. And then the remaining energy is given to the electron. So this is how the electron is seen, moving towards the detector, right? So this expression is to be kept in mind. And now, if you sort of rearrange the expression here, like if you bring this h nu naught, that is the binding energy, that is the energy which binds the electron with the nucleus of the atom, that is h nu naught, you get h nu minus h nu naught equal to the kinetic energy of the electron. Or you can write the kinetic energy of the electron as h nu minus h nu naught. This is finally equal to you can take h as the common factor, nu minus nu naught. So finally, this becomes that is kinetic energy is equal to h into nu minus nu naught. So this is the energy that the electron gets from the photon of light after it is being ejected from the metal surface. That's it. So these are some of the points which you are supposed to know. So as far as the photoelectric effect is concerned, when beam of light strikes the metal surface, when I say a beam of light, it consists of photons. So each photon will have an energy of E is equal to h nu. Nu here is the frequency of a photon of light which is traveling in the form of waves. And now h nu becomes the total energy of a photon of light. And then this energy of the photon of light is used in such a way that one part is used to eject the electron from the metal surface. This is called H nu naught, or it's denoted by H nu naught, where nu naught is the threshold frequency or the minimum frequency. And when you multiply these two, you get the minimum energy required to remove the electron from the metal surface. It's called the binding energy, and the rest of the energy is given to the electron as kinetic energy. That's it. So this is all about the results of this experiment by Heinrich Hertz. And now the next thing is the last part, the most important part, I should say, the conclusion of the whole thing. Now we have talked about the wave nature of electromagnetic radiation, and then next we have also talked about the particle nature of electromagnetic radiations, right? So now ultimately we come to what is known as dual behavior or dual nature of electromagnetic radiations, right? So here we will see that these electromagnetic radiations, they have both these properties, that is of wave-like as well as particle-like. So radiations, at times they behave like waves, at times they behave like particles. So depending on the context or the experiment, I will have to treat electromagnetic radiations either as waves or as particles. So now to conclude with, it is the particle nature of light on the one hand could explain the black body radiation and photoelectric effect satisfactorily. So when you consider the particle nature of electromagnetic radiation, it could explain the black body radiation and photoelectric effect satisfactorily. But on the other hand, it was not consistent with the known wave behavior of light. Now, wave behavior of light, which could account for the phenomena of interference and diffraction of light. So this particle nature of light, could not explain the wave nature of or wave behavior of light, which is seen in the case of this phenomena like interference and diffraction of light. So now it's very confusing here because the wave nature of light could not explain the sort of things like black body radiation and then photoelectric effect. Again, the particle nature of electromagnetic radiation, which would explain radiation, that is black body radiation and photoelectric effect, again could not explain these phenomena, interference and diffraction of light. So it says the only way to resolve this dilemma or confusion, is to accept the idea that light possesses both particle and wave-like properties. It's all very confusing. So the best thing is to accept the idea that light behaves both like particle. Light possesses both particle and wave-like properties. That is, light has dual behavior or nature. But depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Now, since light is a kind of radiation, that light is also radiation. Now, it may be concluded that all other radiations, there are many other radiations, right, behave like waves as well as like particles. So such a wave-like and particle-like nature of light is known as dual behavior of electromagnetic radiation. And finally, it turns out that some microscopic particles like electrons also exhibit wave-particle duality. So these microscopic particles like electrons, they are also said to exhibit this wave-particle duality, that is both particle and wave-like properties. So you will see that these electrons, they're so tiny, electrons are so small that they also exhibit this wave-particle duality or wave like and particle properties are seen in the case of these electrons, which are very tiny or microscopic in nature.